All right, welcome to this lesson, and we're going to be looking at tutorial sheet 1, which involves solving questions on units, measurements, unit conversion, and also dimension analysis. And without wasting time, let's get into question 1, which is saying for each of the following, list 5. For each of the following, list 5: A, base quantities; B, fundamental units; C, derived quantities; D, derived units. So we can answer this question in one simple way, by the way. We can because we know to say base or fundamental units are the units of measurements that are used to measure base quantities, whilst derived units are the units of measurements that are used uh, to measure or to quantify derived quantities. We can just answer these questions in two pairs. We can combine A and B and also combine C and D. But when writing it in your assignment, you have to make sure you distinguish them the way they are. So I'm going to go to my blackboard here. And I'm going to start with A, which is saying base quantities. So not to say base quantities go together with what? Fundamental units. With fundamental units here. So I'll just be putting a base quantity here and its corresponding unit on the other side. Like that. So the base quantities that I'm going to put, one of them is length. The second one will be mass. The third one will be time, since you're supposed to list 5. The fourth one will be electric current. Electric current, the last one I'm going to include is temperature. So remember, there are 7 in total. When you talk about base quantities, there are 7 in total, but they've only asked us to mention 5 of them, and that's what we're going to do. So we have length, and we're going to provide the correspondent fundamental units because we've been asked to say we need to provide fundamental units. So by us just providing the units of measurements for these guys that we've written there, that means we've answered the question B. So for length, the fundamental unit is the meter, represented by a small letter m. For mass, the fundamental unit is a kilogram, represented by the letters small k and a small g there. For time, the fundamental unit is the second, represented by a lowercase s. For electric current, why do these look disorganized? Let's do this. For electric current, this one is for time. For electric current, it's the ampere, amps, represented by the capital A. So remember, these the representatives or the letters that represent the different units of measurements here, you should take note of them because you're going to see the importance of these on question 2. When it's different when you in units of measurement, when you write capital M and small letter m. Small letter m is going to represent mass or the meter itself. Whilst when you put capital letter M, it's more like you are doing the prefixes. And in measurements, capital letter M is used to represent mega. So if you put M or capital M instead of small letter m, that means you've gotten that one wrong. So you should take note of those small observations. Temperature, the fundamental unit of measurement is the Kelvin, represented by a capital letter K. Like this. So you should also be able to differentiate between capital letter K and small letter k, because small letter k represents kilo, whilst the capital letter K represents Kelvin, which is the fundamental unit for measurement of temperature. So those are the answers for question A and question B. This one is question A. This one is the other one is question B. Like that, we've produced the fundamental units or the fundamental quantities, which are also known as the primary quantities or the base quantities, and we've also provided the base units, also known as the fundamental units or primary units. Let's go to question C and D. Question C and D here. These ones, they've asked us to find derived quantities or to list 5 derived quantities. So I'll put here derived quantities. Also on the other side, I'm going to put it derived units. Yeah, so some of the derived quantities that we can talk about, since we've been asked to list 5 of them, I'll talk about speed or velocity. Let me just say velocity. We can talk about acceleration. We can talk about a force. We can talk about pressure. we can talk about volume. So if you remember what I talked about last week in class, I explained to say when you're talking or when you're dealing with the derived units for the derived quantities, you have to understand which fundamental quantities are producing or are coming up with that particular derived quantity, because your base units, or rather the SI units for your derived quantity, are going to come from that knowledge. We're just combining the units that we are using in the base quantities or in the fundamental units to come up with these units for the derived quantities. So I'll say for velocity, velocity is equal to distance over time. So that means the units for velocity are going to be what? Are going to be meter per second. Now, I don't know if I'll be writing everything here. Meter per second, which will be meter per second like this. For acceleration, this is meter per second squared. I'll say meter per second squared, which will be like this. Yeah, for force, force is equal to mass times acceleration. If you want to calculate force, you use the formula mass times the acceleration, but the SI unit for force is the Newton. Newton, represented by capital N, capital N rather. But as I said, it is also expressed in mass times acceleration, and you know how to find the units for mass times acceleration. Pressure, pressure is equal to force per unit area, but the SI unit for pressure is the Pascal. Then we have volume. The SI unit for volume is the cubic meter. So cubic meter. Oh, this one is capital A, or capital P, and a lowercase a. Whilst for volume, it's the cubic meter. This one is simple. Almost all of you know it. So we have a small letter m to the power 3 like that. So those are some of the derived units, and this some of the derived quantities that we can look at. We've only been asked to mention 5 of them, of which these are a lot of them. The derived quantities are a lot of them. But since we've only been asked to find or to give 5 of them, those are the ones. And hence we've answered question 1, which is talking about listing 5 of each of the following: base quantities, fundamental units, derived quantities, and also derived units. And that means we're done with question 1. We can move on to the next one, which is saying write the full names of the following units. Write the full names of the following units. So very important. We already talked about this last week. These are prefixes. So they've just combined some of the quantities, of the physical quantities, or the units of measurement with the prefixes, which you said are used to handle or to simplify things when you're dealing with very large or very small measurements or readings. So let's get into it. Let's give the full names of the following units. So that's question 2. And the first unit we've been given is this one. We have 1. So say this symbol represents micro, whilst the small letter g is for a gram. So which means the full name for this unit is microgram. We also have the second one, which is a capital M and a small letter m. So we said when you look at, or when you see a capital M, it represents mega, whilst the small letter m always represents a meter. So this one is equal to what? This one will give us a megameter. Then we have this one, a small letter k and a capital letter K. So we said when you find a small letter K, it represents kilo, whilst a capital letter K represents Kelvin. So this one is kilo Kelvin. You have another one, which is a capital or a small letter m and a capital letter J. Whenever you see a capital letter J, that's for joule, whilst a small letter A is used to represent nano. So this one is a nanojoule. A nanojoule. Then there's another one, which is a small letter d and a small letter m. So a small letter d is always representing a deci, whilst the small letter m is for the meter as usual. So this one is a decimeter. we have a capital letter T and a capital letter C. So a capital letter C or a capital letter C is used to represent the coulomb, whilst the capital letter T is used to represent stellar. These are just prefixes. If you've forgotten about this, just go back to that table that I displayed to you the other day, where we're looking at the different prefixes, the most common prefixes and their symbols. So the capital letter T is for tera, whilst the capital letter C is for coulomb. So I'll say tera, coulomb, like this. Then the last one, we have a capital letter G and a capital letter A, of which the capital letter G always represents giga, whilst the capital letter A is for ampere, the SI unit for measurement of electric current. So I'll say giga, ampere, like this. And just like these guys, we've mentioned the full names of each of these units that have been given here on question 2. We have 1, 2, 3, 4, 5, 6, 7. And I hope we've given 7 here. 1, 2, 3, 4, 5, 6, 7. Okay, so that means we are done with question 2 also, just like that. We can move on to the next question, which is our question 3. Question 3 is saying an aircraft flies from London to Sydney in a time of 21 hours, 40 minutes. The distance traveled is 17,000 kilometers. What is the average speed of the aircraft? What is the average speed of the aircraft? So this is a very simple question. We're supposed to find the average speed, of which the formula for average speed, this is question 3 actually. The formula for average speed says average speed is equal to total distance traveled over total time taken over total time taken. And they've given us the distance that has been traveled to say this is 17,000 kilometers. Well, let me just write it like this. Say distance. Distance is equal to 17,000 kilometers. Whilst they've also given us the time that the plane takes in flight, which is 21 hours, 40 minutes. Like this. So what I was supposed to do in order for us to find the average speed, the first thing we can do is convert the distance into meters, since the meter is the SI unit for distance. And we can also convert the time into its seconds. So how are we going to do that? We already explained how to convert units from one unit to another. So what are we going to do? We're going to say this 17,000. You just put, okay, here, 17,000 kilometers multiplied by the conversion factor of a meter, of a kilometer to a meter. So these are kilometers multiplied by the conversion factor, of which the conversion factor is just a ratio, which is going to give us exactly 1 unit of the other. So I'm going to say multiplied by 1 meter, which is equal to 10, or times 10 to the power minus 3. Or I can just write it in this form to avoid complications with the powers. I can just say 1,000 meters, which will give us 1 kilometer. The kilometer and the kilometer are going to cancel out, and I'm going to multiply this 17,000 by 1,000 meters. So this is going to give me how many meters? Let me just punch into my calculator. 17,000. Okay, so I'm getting my total distance as 17. This is quite a huge number. So this is our distance in meters. And the second thing we can do is find the time, or also convert the time into seconds. So what are we going to do? We're going to multiply the 21 hours that we have by the seconds that are in 1 hour. So 21 hours multiplied by 3,600 seconds, that make up 1 hour. So the hour and the hour cancel out. 21 by 360. I'll say 21 multiplied by 3,600. This plus the 40 minutes that we have here. So the 40 minutes are also going to be 40 multiplied by 60 seconds. Hence, our time, this is our distance. Our time will be equal to, okay, 78,000 seconds. 78,000 seconds. Okay, so we found our time and our distance in their S or in their respective SI units. Now, what are we going to do? We're going to plug them into the formula. So I said average speed or average velocity will be equal to total distance traveled over total time taken. So I'll put my 17 like that divided by 78,000. That will cancel out, and our average speed is going to be equal to what? It's going to be equal to 17,000 divided by 78. This is giving me 217.94. 217.9487. I can just say 949 meters per second. So that means that is my average speed. But if we look at the values that have been given, since this is a multiple choice question, the values that have been given here are 2.2 meters per second, of which this is not true. We found 217.949 meters per second. So option A is incorrect. Option B, 2.2 times 10 to the power 7 micrometers per second. C, 2.2 times 10 to the power 11 nanometers per second. D, 2.2 times 10 to the power 6 millimeters per second. So this is the tricky part about this question. We need to convert the answer that we've been given or the answer that we've calculated into all of these units that we have here. And that's how we can tell which one is the correct option between these. Since our answer has been found in meters per second, and we've already discovered to say option A is not the answer in this case. So that means the answer can either be option B, C, or D. So we need to convert our answer that we've been given into these various units of measurements that we have here, which is the micrometer per second, the nanometer per second, and also the millimeter per second. So let's do that. Let's do this. So we're trying to check if option B is correct, of which how we're going to do that is by converting this guy into micrometers per second. So 217.949 meters per second like that. I'm going to multiply this by the conversion factor of a micrometer to a meter. Okay, so how are we going to do that? We know to say 1 micrometer is equal to 10 to the power negative 6 meters. 10 to the power negative 6 meters. So this is the conversion factor that we are going to use here. Or in other words, we can say 1 meter is equal to 10 to the power 6 micrometers, like this. So this is the conversion factor that I'm going to use here to convert 217.949 meters per second into micrometers per second. So let's use either of these. Just rub here. So I multiply it by okay, so I multiply it by 10 to the power 6 micrometers over 1 meter. So this will cancel out with this, and I can multiply 217.949 multiplied by this guy that is on the right hand side. Okay, and I'm finding an answer which is equal to 2.2. I'll just round it off to its scientific notation. I'm finding okay, so we have 2.2 times 10 to the power 7 micrometers per second. This is option B. This is option B. And if we check what we've been given on option B, saying 2.2 times 10 to the power 7. Oh no, sorry. So instead of me calculating, I've gotten this one now. It's the one that I've put here. I've written this exact thing on my board here. Let me punch it again. Let me punch it again. Yeah, so 2.17. It's giving me something very, very huge. Very, very, very huge. Okay, so 217.949 multiplied by 10 to the power 6. Okay, so it's giving me an answer which is equal to 217.949.000 like this. So which means if I write this into scientific notation, I have 1, 2, 3, 4, 5, 6, 7, 8. So this means I can say this is 2.2 times 10 to the power 80 micrometers per second. Okay, so that means option B cannot be the answer because option B is this one that is here, and the one we've calculated is this one, which is option B is also too small to be our actual answer. We have another one, which is converting this same answer into nanometers per second. Okay. This is quite tiresome. So let's convert our 217.949 meters per second into nanometers per second like this. So the conversion factor is that 1 meter is equal to 10 to the power 9, not negative, 10 to the power 9 nanometers like this. Or we can say 1 nanometer is equal to 10 to the power minus 9 meters like this. So this is the conversion factor that we're going to use to convert. So I'll say 217.949 multiplied by, this is meters over second, multiplied by, I'll use the simplest one to use, which is this one. Now multiplied by 10 to the power 9 nanometers, which will give us 1 meter. So the meter and the meter will cancel out, which means I'm multiplying this same guy by the power 9 now. And it's giving me an answer which is equal to 217.949 with that amount of zeros. So if I write it in scientific notation, this is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this will be 2.2 times 10 to the power 11 nanometers per second, like this. And if we check the answers that we've been given on option C, okay, so it's exactly the answer that we have on part C. So that means part C is the correct answer. Part C is the correct answer. We don't even have to waste time to convert this same answer to option D because we've already found the correct answer. So the correct option is option C, exactly what we have here. All right, so that was question 3. Now let's go to question 4. Question 4 is saying consider the formula P is equal to K EV squared over Q, where P is equal to power, E is equal to energy, V is velocity, and Q is charge. What are the SI base units of K? What are the SI base units of K? So what are we going to do here? We've been given this question, and we're going to use, or we need to perform a dimensional analysis based on the units of the other physical quantities that are in this same equation in order for us to find the base units of K. So I'm going to bring this equation here. So we have P being equal to K EV squared over Q. So P, they said, is equal to power. The SI unit for power is watt, but the base units are kg. Meter squared second to the power 3, to the power minus 3 rather. Then we have E, which is energy. The SI unit is the joule, but the base units are kg. meter squared, second to the power minus 2, like this. Then we have Q, which is for Coulomb, or the SI unit for Q, which is charge is Coulomb, but the base units are ampere multiplied by second. Then we have V, which is just for velocity, so this is meter per second. But since they've given us to say it's squared, we're going to say this is m to the power 2 multiplied by second to the power minus 2, like this. So this is the one that we're going to use. So from this equation that we've been given, let's make K the subject to the formula. So we're going to say over 1, we're going to cross multiply, and at the end of the day, we're going to end up with K is equal to PQ over EV squared. And we can plug in the base units from here. So the base units for P are kg meter squared over second to the power 3, like this. And I'm multiplying this by Q. Q is just A, which is for ampere, like that, then over EV squared. So E is kg meter squared over second squared, and this is multiplying to meter squared over second squared, like this. So we can now simplify this equation, of which what are we going to remain with? You know, to say K here is going to cancel out the K that is here, since they are both numerators. We have S here, S squared, which is here, which can cancel out with the S power 3, which is here, only leaving us with the 1S. So I can say this has cancelled out. We've remained with only a single S there. Then what else? We have M squared here. We can cancel out with the M squared that is there. Then what else? We're remaining with S here as a denominator. Let me just simplify it here. So our K is going to be equal to, we have S power minus 1, and this is multiplying to A multiplied by S, like this, over, what do I have here? Here everything else has cancelled out, but on the other side I'm remaining with M squared, like this, multiplied by S to the power 2, like this. Okay, so this is the simplified version. Now let's simplify it further. This is to the power minus 2. This is minus, not squared. Okay, that is minus 2 there. Can simplify this guy further. This is the denominator, this is the numerator. This can cancel out. That means we're having our units of K as A over M squared S to the power minus 2. So since this one is the numerator here, what are we going to have? We're going to take, this is the final. We can leave it here. This is still correct, but we can write it as K being equal to A M to the power minus 2 S to the power 2. So these are the SI units of, or the base units of our constant K in the equation. And just by doing that, you will have gotten everything correct there. So that was question 4. We can now move on to question 5, which is the last question. Question 5 is saying convert the following units: 300 millimeters to mega meters, 300 millimeters into mega meters. Then part 2, 250 nanometers, square nanometers into square centimeters. So what are we going to do here? This is also a very simple question involving unit conversion. This is question 5. Yeah, so that is question 5. Part 1 is saying we convert 300 millimeters to megameters. So what are we going to do? We're going to multiply these guys by a conversion factor. And one thing we have to know is that 1 millimeter is equal to 10 to the power minus 3 meters. And also that 1 megameter is equal to 10 to the power 6 meters. So using these conversions now, we can convert our millimeter directly into nanometer, because what are we going to do? We're going to do the summation of the conversion factors, because this is the same as you're having 10 to the power 3 millimeters being equal to 1 meter, like this. So which means 1 megameter is actually equal to, you add this and this, or you multiply them, not adding, sorry. You multiply these two, you're going to get 10 to the power 9 millimeters, like that. So this is what I'm going to do in order for me to convert, or this is the unit factor that I'm going to convert that I'm going to use to convert 300 millimeters into megameters. So let's do this. We have 300 here. I'm going to multiply them with 1 megameter, which is actually equal to 10 to the power 9 millimeters. So these are millimeters, sorry. That millimeter is going to cancel out with that millimeter. Then we're going to say 300 divided by 10 to the power 9. 300 divided by 10 to the power 9. And this is going to give me 3 times 10 to the power minus 7 megameters. So 300 millimeters is equal to 3 times 10 to the power minus 7 megameters. That's part A. Part B is going to... So for us to convert part 2, which is saying 215 square nanometers to square centimeters, are just going to use the squared conversion factor between the nanometer and centimeter itself. So we're going to say, we know to say 1 nanometer. 1 nanometer is equal to 10 to the power minus 7 centimeters. So we're going to square this conversion factor. Then we're going to use it to convert our square nanometer into square centimeters. So I'm going to have 250 square nanometers multiplied by 10 to the power minus 7 centimeters over 1 nanometer. Then I'm going to square this conversion factor. And if I square it, what do I get? I'm going to get, let me just write the squared version of the conversion factor directly. I'm going to remain with 10 to the power minus 14 square centimeters over 1 square nanometer, like this. So the square nanometer and the square nanometer will be able to cancel out, such that I'm multiplying the 250 by the 10 power minus 4 square centimeters. And by so doing, I'm going to get 2.5 times 10 to the power minus 12 square centimeters. And by that, ladies and gentlemen, we're done with Tutorial Sheet 1. That's the end of Tutorial Sheet 1. You can go back to the previous videos to solidify on your knowledge on units and measurements, and subscribe to the channel, and also like the video and share with your friends. Thank you very much. This is Tita John. Until next time, stay blessed.